Great. Thank you. Thank you so much for inviting me. It's a nice sunny weather outside, so thank you for spending your time inside listening to me. Yeah, so my name is Gowatham Kaki. I know my first name is a bit hard to pronounce. It's my students call me Gotham from Batman, so I'm okay with that. So what I want to talk about is a problem of distributed convergence or convergence in distributed systems and how it's related to consensus in distributed systems, right? So this talk should have ideally been named as distributed convergence is halfway to distributed consensus. But yeah, the title is too long, so just cut it down to convergence is halfway to consensus. Okay, so I'm an assistant professor at CU Boulder. So my work is primarily in formal verification. So essentially, formal verification is this area wherein we try to look at the software and try to generate mathematical proof that the software is in fact correct, right? There is no way the software can go wrong. So it's generally used in safety critical applications, but these days it's seeing increasing adoption in blockchain space as well, right? So my colleague Molly Sagev essentially does this sort of work for smart contracts and stuff. Anyway, so let's come to the topic of today's talk. So okay, so I'd like to start with this picture of replicated state machines, right? So replicated state machines are essentially one of the first foundational abstractions of how a distributed system should look like. So this was back in 70s and 80s when people like Lamport, Fred Schneider, Nancy Lynch, etc. So when they were looking at when they first started sort of trying to connect computers together and see how this system of computers should actually look like, or how a user should perceive this system of computers, they came up with this mathematical model. They said, well, they should look like a machine, a single machine, as an abstraction from outside. So it's a machine with it's a state machine because it goes to different states, and it's a replicated state machine where the state is replicated across various nodes, machines, or whatever processes. You can take your pick. So the idea is the state is replicated across various places, and when a user, let's say, submits an operation, the operation is sort of immediately applied at all the replicas, right? So each of this node is called a replica of the state. So the operation is applied at all replicas and instantly sort of appears everywhere, right? So let's say Alice submits, we had this state and Alice submits operation C. So you get state S4, right? And S4 is this current state on all the replicas, including the remote replica B, right? Remote node B. So later on, let's say Bob comes and tries to read from a different node, right? Bob actually sees the latest state S4, right? So it sort of worked as if both are sort of contacting to a single machine, right? So this is the abstraction that initially people thought distributed systems should actually adopt. So this is a replicated state machine abstraction, right? And if Bob submits a D operation, again, it sort of immediately gets reflected at both the nodes or both the places, right? Okay, great. So this is the property that replicated state machines offer has come to be known as strong consistency, right? So this is, or otherwise known as linearizability, sequential consistency, or whatnot, right? So effectively, that means to say that, well, what you're doing makes sense, or it's a consistent. So the state always moves in a lockstep fashion in one state at a time, like one step at a time. So there's always a way to linearize your entire set of operations, right? So that was the abstraction. The strong consistency was the abstraction, and replicated state machines was the mathematical model that was supposed to represent distributed systems, right? But that's the theory. What happens in practice? Well, in practice, there's no free lunch, right? So you have these machines or replicas spread across unreliable networks. Maybe they are geo-replicated or geo-distributed. So when Alice, let's say, submits an operation C to a replica A or node A, it gets executed. You get a new state S4, but there might be a transient network fault. So your C may not actually reach the different replica, right, or different node. While in the meantime, Bob might come and contact the different node, right? And so even though Bob is later in time to Alice, he still ends up reading an earlier state, right? So S3 here, for example. So, and if Bob submits a new operation, it gets applied to the old state S3 and not the quote-unquote latest state, right? So we now have certain common history between Alice and Bob, right? So S1, S2, S3. but Alice ends up creating a new state S4 from S3, and Bob ends up creating a completely different state S4 prime from S3, right? So this is not, if we were having an abstraction of a single machine or a strongly consistent machine, we wouldn't have seen this behavior, because Bob's operation, since it's later in time compared to Alice, it would have been applied to S4, and we would have gotten a late, an actual S5 state, right? But here we actually have a competing successor states for S3. You have S4 and S4 prime. So this is not the replicated state machines are supposed to produce. But in practice, if we let the distributed system be by itself, this is how things are going to pan out, right? So this is what is usually referred to as weak consistency or eventual consistency. Sorry, not eventual consistency. Let's stick with weak consistency, because eventual consistency, I'm going to use it for a different thing today, right? So yeah, this is practically referred to as weak consistency or lack of consistency. Let's say that. Okay, so then how do we get the replicated state machine abstraction in practice, right? In theory, it's all fine. How do you get it in practice when you have network that is unreliable and all of that, right? So let's say you want this system of 3 machines or nodes A, B, C to work as a single system, right? So Alice, let's say, submits an operation C, right? There must be some sort of consensus among these machines on what state the operation should be applied to and what should be the result of this operation, right? So let's say there was some consensus, and then all the nodes agree that the next state through S3 is in fact S4, right? Then later on, Bob comes and submits a different operation, or reads current state. So since all the nodes sort of agree that the current state is S4, Bob ends up reading the current state. And finally, if Bob sort of does an operation, it is indeed applied to the, and even that involves a round of consensus. So all the nodes should sort of huddle together and make a decision on whether Bob is applying this to the current state, and what the result of this operation should be, right? So if there's a consensus, then if all nodes can be on the same page and say that, well, S5 is the final resultant state, and so on, right? So you can simulate replicated state machine abstraction in practice on unreliable networks using consensus, right? If you can somehow get the nodes to be on the same page, right? Which is essentially arriving at a consensus, right? There should be an asterisk here, because consensus is not always possible in practice, but that's a different question, right? We'll get to that. So, but then people have the distributed systems researchers such as Lamport and so on. So they worked on various what are known as consensus algorithms, right? So these are protocols where various machines can sort of talk to each other and arrive at a consensus on what the result of an operation is, or what the next state of of the system is, right? Or the next entry in a log is, and so on. So we had starting with I think 98. I mean, we had view stamp replication back in 88 or so. Yeah, view okay at all 88. But since 80, so we had like a lot of consensus algorithms, right? So all of them implement a slightly different form of consensus. So like each of that is essentially about getting all the nodes on the same page, but some of them operate on a log, some of them operate on a series of states, some of them operate on a single state, and so on, right? And of course, each even in the latest key value store databases and so on, like for example, CockroachDB, TickVDB, and or Tiger Beetle, and all of these databases. So they end up implementing their own sort of variants of consensus protocols, such as Paxos and Raft, that are specialized for their own cases, right? Okay, so this is good. Things have been going well. But the problem with this sort of consensus protocols in general, right, or consensus algorithms, or the consensus as a feature, right, in practice, is it is impossible to guarantee availability of a system that relies on consensus, right? So this is not sort of a practical, or it's not sort of just an experimental observation or an empirical observation. It is in fact the result of a famous theorem called CAP theorem, right? So there was this thing Eric Brewer conjectured in 2002 that it's not possible to have partition tolerance and availability at the same time if you're trying to be consistent. And later on, Nancy Lynch and Gilbert sort of ended up proving that result, right? So it's not just hard, but it's rather impossible to have availability in the sense that being always available to your users, right? So it's impossible to guarantee availability if your system relies on consensus, right? But it's also hard to guarantee correctness, because these protocols are some of the most complex control flow things, systems that you'd ever see, right? So if you look at even the simplest variant of Paxos, to actually appreciate various edge cases and actually get everything right, it's going to take a while, right? So, I mean, you should maybe look at how the graduate classes on distributed systems actually pan out. So the first version of Paxos algorithm that students end up writing is almost invariably incorrect, even though they have seen it like 100 times, right? Because there are so many sort of subtle things that people tend to ignore and all of that, right? So yeah, because these things are really hard to get right, people try to do formal verification. So there have been a lot of efforts of doing formally verifying specifications and implementations of consensus algorithms. So in theory, it's all good, but in practice, this is formal verification is a really expensive exercise. So it ends up taking a lot of time. So I've sort of put in a slide. So this is a slide within a slide. So this is a slide that I've taken from my students' talk. So he sort of has this bunch of papers that focused on formal verification efforts on distributed protocols, and sort of have picked the quotes from these papers, right? Like for example, this Iron Fleet paper is from Microsoft Research. They ended up spending 3.7% years to prove a bunch of protocols correct, right? And this is Woos et al. Is a work proving Raft implementation of Raft correct in a theorem prover called Coq. And although it's just basically for 530 lines of code, the actual number of lines of proof to show it correct is 50,000, right? So it's a order of 100 blow up over the code size when compared to the proof size when compared to the code size, right? Okay, so this seems to be clearly not practical. So the things that are in front of the challenges that we have are, can we sort of avoid this strong consistency or consensus in our systems when we are building distributed systems, so that we don't have to deal with this reality of not having availability, right? So if it's not possible, if you have to really implement consensus, can we at least sort of get it right? So can we sort of make our tools intelligent enough for formal verification strong enough that we can verify these protocols or implementations with little effort, right? So these are the key questions that are generally explored by the distributed systems and formal verification community. These are also the things that I work on. So okay, so this is with respect to these questions, what can be done, right? So let's consider the first question, right? So is it possible to avoid strong consistency or consensus and still build a useful or a practically practically usable system, right? So let's go back to our previous diagram. So we had this bunch of states. There is a network sort of transient network error. So the state S4, which was created by Alice on the left side, and S4 prime created by Bob on the right hand side. So these are sort of competing states, right? So they're not in sync, right? So these machines are actually not in sync. So when the network sort of heals, right, then let's say you can send the operation C over to the other side, right, and D over to this side, right? So sort of you send both operations over to both the nodes, right? So let's say, right, C and D are such that although they sort of initially created states S4 and S4 prime, which are different, but when they eventually get applied, right, they both end up creating the same state, right? That is, for example, here we had my pointer is not working, I guess. Oh yeah. So we had C followed by D, and here D followed by C, and still we sort of end up with the same state, right? So let's say we had this scenario, right? So then you don't have to do much, right? So you could sort of let the actions propagate and apply it in different orders, and you kind of end up with the same state anyway, right? So this property is called commutativity, right? So commutativity is essentially operations F and G on a data type T are commutative if and only if they have applying them in any order results in the same result, right? Same state. So if you have a data type where all operations are commutative, then of course you can sort of execute them in any order, right? And the network might heal or it might not heal, but eventually everyone is going to end up with the same state, right? So yeah, that is at least better than it's still not consensus because there is a transient disagreement between these things. So for example, meanwhile, before convergence, let's say someone contacts node A, they get S4 as a result, and someone contacts node B, then they get S4 prime as a result. So it's still not consensus, but it's still nothing. Something is better than nothing, right? So eventually we got a at least eventually you're going to get to the same state. So this is still better, right? So yeah, so this is the intuition behind what are now known as conflict-free replicated data types, or CRDTs, right? So the intuition is, well, if your data type has all commutative operations, then they're going to eventually, you can apply them in any order, and then things are going to eventually converge, right? So that was the paper from Shapiro and others, which introduced the CRDTs. So as a simple example, we have a counter where we have an initial value, right? A counter, let's say it supports only additions and subtractions. For example, let's say you're just having a counter that counts the number of likes on your post, right? So you don't need to have strong consistency for that, because your additions and subtractions, they could be done in any order, right? But eventually you could, they because additions and subtractions sort of commute, you end up with the same result everywhere, right? Eventually, when the network heals and all the operations are sent over. So although you might see, let's say your friend might see different number of likes on one post compared to yours, eventually you both are going to see the same result, and world is not going to end in the meantime, right? So this is okay, right? So that's a simple counter CRDT. So commutativity ensures convergence here. Convergence is eventually having the same state. But commutativity in general is not a common occurrence, right? So here, I basically shown an execution, right? We'll come to this execution, but essentially the intuition here is, let's take a set, right? A set data type. If you're trying to insert and remove an element T at the same time, right? So you could execute that insertion or addition and removal in different orders, and you end up with a different result, right? Because add and remove on set do not commute. So in this specific execution, you have both replicas start with the same singleton set. You have remove on the both sides, but here on the right side you have an add again, right? So when everything gets propagated everywhere, things get executed in different orders. So here it's remove, and add. So you have finally E being in the set, and here it's remove, add, and remove. So you have nothing in the set, right? So this is just me sort of trying to convey you that not everything can be commutative, right? And in practice, there are things that are useful and things that that cannot be commutative, right? So the what CIDT people then say is, oh well, you can sort of find out which things are, like if there are non-commutative operations, maybe at the runtime you could detect the conflicts, and you can force an order among them, right? So in this case, for example, add and remove are conflicting operations and they are concurrent. So you can sort of try to make add win or remove win, in which case you get an add win set, what CIDT people call as add win set or remove win set, right? So this works for this particular example, and also a few other examples, because the actual being in a set and not being in a set is just a binary decision here, right? So for these sort of things, having an arbitration order of trying to break ties by letting one operation win or the other, that seems to work, right? But in general, though, this approach seems to have limitations, right? So hit me up offline to discuss what the limitations are, and I think Thomas has encountered one such limitation in his work, right? So while we were thinking about it, we thought, oh, let's sort of see if there's a different sort of alternative approach that we can adopt without when there is no commutativity, like without having to rely on commutativity, right? So to understand what that approach could be, an alternative approach could be, we'll go back to this situation where we had diverging states S4 and S4 prime on both the replicas, right? So let's say C and D are not commutative, right? But if you sort of put these two states or these two histories together, right? What would if C and D are not commutative? So if you put these two things together, you can see that they have some common history, right? And then there is certain divergence at some point, right? So there is common history and then divergence here and divergence here, right? So if, let's say, regardless of what C and D are, or C and D need not be even a single operation, it could be a series of operations, right? If you can somehow sort of merge these two states into a single state, right? Then you don't even have to re-engineer your data type in terms of commutative operations. You just need to write a merge function on your particular type, and you should be good to go, right? You'll eventually get convergence, right? In other words, if you have a guarantee that you can merge any two diverging states of your type or diverging values of your type, provided that there is some sort of common ancestor, right? Let's say if you have such a guarantee, Then you can apply this merge function any number of times. So you can eventually converge to the same state, right? So if you just focus on what's relevant here, you have this diamond diagram where you have the common ancestor state and diverging states and the merge state. So if this might look sort of relevant or this you might have a sense of deja vu here because this looks sort of quite close to how you do git merge, right? So you would have a common ancestor version, your friend has his version, and you have your version, and when you merge it, you have the same version, right? So indeed, so this entire approach was inspired by Git, right? So Git version control system. So yeah, so this was so we built sort of a version of replicated data types like CRDTs, but instead of basing that on commutativity, we based it on Git style merges. So we started calling them as mergeable replicated data types, right? So as an example, here is a simple set, right? You might have done any number of operations. So you started with set 1, 2, 3. On the left hand side, you sort of subtracted or removed 3. On the right hand side, you removed 1 and added 4. So you have two different sets now. But now, so the intent there is essentially captured by removals and additions, right? But let's say you can merge these things by just preserving the intent, right? Then you would eventually have the same state. The preserving the intent here being that removing 3, right? The user intent is to remove 3, remove 1, and add 4, right? So if you do that, you'll end up with the same state, right? And this can be done by writing a simple merge function. Let's say you have common ancestor state S and two diverging states S1 and S2. You can retain the common elements in the final merged version. So in the merged version, you can retain the common elements in all that are never deleted. Then you can add the newly added elements in S1 and add the newly added elements in S2. Voila, and you just get the final the resultant state, right? So take any set implementation. No camel, OCaml is my language, but let's say Python or something. Just write a three-way merge function. That's it, and you're done, right? And you could just rely on Git infrastructure to just get your replicated data types up and working, right? So this was an approach that we explored, as I mentioned in a paper. So how general is this approach? Well, it turned out that you could reduce the merge function of any data type into set merge, right? So theoretically, there exists a decomposition from any data type merge function to a set merge function. So if you know how to merge sets, you know how to merge any data type, theoretically speaking. But that's just a theoretical result. Doesn't mean that in practice it's efficient to just reduce it down to sets and merge it. But we just want to show it's general enough, right? So here are all the data types for which we just sort of synthesized or automatically derived merge functions, starting with the set merge, right? And we also wanted to see if this approach is even practical. So we sort of implemented it on top of an existing data store. So we didn't want to do the network layer by ourselves. We just relied on ShylaDB and put our entire thing as a soft shim layer on top of ShylaDB, and things seem to just work. So here are, you don't need to understand these graphs, but these are just to show you, just to give you some assurance that we have done the work. We have done the work. We have seen that these are in fact practical, right? So yeah, this thing seemed to sort of work in practice. But this was back from 2019 and 2022. Okay, so yeah, and of course, a few blogs seem to have picked up this thing as well. So it trended on the Orange website for a couple of days. Right, but are we done now? Right? Well, not yet, because as I mentioned before, convergence is not consensus, right? To put it succinctly, convergence is about eventually agreeing on some value, and consensus is about never disagreeing on values, right? So convergence doesn't mean consensus, because here you might eventually agree on some state S5 or something, but meanwhile you intermittently disagree on these values on what state is, like S4 and S4 prime, right? So consensus is about never disagreeing, right? And why is that important? Well, let's say you're maintaining a bank balance, right? Or you're replicating a bank balance, bank account, and so on. So two ATMs should not disagree on your balance. Otherwise, you end up sort of having a double spending errors, essentially, right? So consensus is in fact important in practice. There are operations that you cannot reduce to convergence all the time, right? Like this, for example, before it converges, you end up reading inconsistent states, right? So let's say you want to really implement consensus. What would you do, right? So previously, the approach was, well, throw your hands in air and say, well, convergence is not enough. We're going to throw everything away and start from scratch, implement our raft algorithms, Paxos algorithms, and all of that, right? But recently we sort of found out that you don't have to really do that, right? You could sort of start your, you could take your system that guarantees convergence and build your consensus on top of convergence, right? So this is not just the theoretical result, it's also practical. I'll explain why it's practical in a while. But let me sort of demonstrate the intuition there, right? So let's say you started let's consider this simple example of leader election, right? Which usually happens in systems like Chubby Zookeeper and so on, right? So leader election is an example of consensus. Everyone has to agree on who the leader is. No two nodes can ever disagree. So let's say if you started with all the nodes having no leader, and you eventually have a single leader, right? So you have initially nothing, and then they go through various states, and eventually everyone has the same leader, let's say, right? So you can say this, we have convergence, right? But that doesn't necessarily mean consensus, because in the meantime, they might have disagreed on who the leader is, and during that time, all the hell would have broken loose, right? Because someone, if let's say if node A thinks C is the leader, they would have sent all the operations to C, and if C thinks B is the leader, they would have sent all things to B, and so on and so forth, right? So, so this is not consensus, right? But if you look at this picture and see, hey, what's actually missing here? Like, okay, I have convergence. If only, if is there any property that I can add to these things so that these two things put together is going to give me consensus, right? So that was the question we asked, and turned out that what we are missing was monotonicity, right? So if a node made a decision about a leader, right, then the decision should never change, essentially, right? So that's essentially like when monotonicity is effectively sort of going upwards in a lattice of your decisions, right? So here lattice is just a two-step lattice. You have no decision or one decision. So decisions should never change, and nodes should eventually converge, right? So our intuition is, if you can somehow, right, show that your system, the protocol that you've concocted, has both these properties, convergence and also monotonicity, then it invariably follows that your protocol also can guarantee consensus, right? So that was the intuition, right? So convergence and monotonicity implies consensus, right? So that was the theoretical result, but why is it relevant in practice? Well, convergence, as I mentioned, your systems most often, you would have built your systems for convergence because it's enough for most cases. You could sort of simply bolt on consensus right on top of convergence on your already existing system. So it's sort of it's little effort, but it's not even that, right? So it turns out that if you implement your consensus algorithms this way, formal verification becomes a lot easier. We were quite surprised with this result, actually, because we actually we implemented this in a DSL called SuperV in Haskell, and we came up with this verification algorithm, and with just very little input from the user, from us being the actual user, we were able to completely verify the implementations, not just specifications, the complete implementations of these protocols completely automatically, right? So that's number one result, right? So a verification becomes a lot easier, so formal verification. But secondly, since we were, we expected, because we are sort of doing extra steps, we are sort of ensuring convergence before doing consensus. We expected our things to be slower than the handwritten implementations, right? But it turned out that our implementation, like here, this is a version of comparing or results comparing latency and throughput of our implementation, which we call as Ferry, written using our style. And this is the HCD Raft, right? So I'm assuming you guys are familiar about HCD Raft, which is Raft protocol used in Kubernetes and so on. So it's written in Rust, supposed to be very efficient and so on. So we ended up being more high performant than the handwritten version on HCD Raft, right? The reason turned out to be quite interesting. It's because we had in the means of, while implementing consensus on top of convergence, there are certain things that you can assume that you cannot assume in a handwritten implementation, and making that assumptions, you can cut down on a couple of round trip times, right? RTTs between the nodes. So if you cut down on a couple of round trip times, eventually things are going to sort of speed up, right? We end up producing a lot more messages than handwritten Raft, but in data centers, the network is not saturated. They have high gigabit bandwidth networks, so you can produce an order of magnitude more messages. It doesn't matter. But if you cut down on round trip times, it actually does matter, because you now have more throughput or less latency, right? So it ended up being, to our surprise, more efficient than the handwritten implementations. Yeah, so that's Super V. That the tool is called Super V. I apologize for the name. It's something my grad student has chosen. So yeah, so the conclusion is distributed consensus is expensive and hard to get right. Convergence is weaker than consensus, but cheap and easy to implement. So it can substitute consensus in surprisingly many cases. So that was the summary of 2010s in distributed systems. Right? So it can consensus could substitute. So convergence could substitute consensus in surprisingly many cases. So on that note, we had this contribution called MRDTs, mergeable replicate data types, and implementation called Quark. And when consensus is unavoidable, it can be implemented on top of convergence. You don't have to do it from scratch. And this approach results in efficient implementations that can be formally verified with little effort, right? And the tool corresponding to that is Super V. You can find it on our labs repository. So that's all I had to share today. I'm sorry I'm 5 minutes over. If you have any quick questions, I'm happy to answer. Yes, Thomas. Yeah. Yes. The simplest one is the like counter, for example. I mean, in general, if you're trying to implement a counter or a bank balance thing within SQL database, you would have said, well, there's something called balance, and you would have written a transaction that said, read the balance and then update balance where bal equal to bal plus 100 in something, right? So that would not actually, converge. I mean, there, if you actually, for that implementation, you do need consensus if you do it in a distributed system. But if you sort of end up implementing it in terms of just the counter and so on, right? Like counter and all of that. For that, you don't need, you could just sort of have convergence and eventually everything's enough, right? So another example is shopping cart. It's Dynamo paper from 2007 from Amazon. So where they implemented their shopping carts as weakly consistent set, like the add removes or add win set. That is another example, right? Yeah.
Media.
So yeah, this would be. I mean, these are all less safety critical applications, right? So just to be clear, when I say can substitute consensus, it doesn't mean that you could, if you have safety critical thing that world can blow up in the meantime before it converges, then that's not the right use case for your CRDTs or MRDTs, right? But there are many use cases where people thought that they would need strong consistency, but turned out you don't need it, right? So TPCC is one long-standing benchmark in databases. When it was converted to distributed world, people implemented everything using strong consistency. But then Baylis et al. And others came along in 2013 and said, well, you don't need it. There are just a couple of transactions for which you need strong consistency. Everything else is just, you could do CRDT style, right? So there are many such results of that form. Looking back, it might look obvious, but at that point, it wasn't. But yeah, that doesn't mean that convergence is all you need. No, convergence is not all you need. You do need consensus, right? Anyone, especially this community, should appreciate that fact because you guys work on blockchains and stuff, right?
In the crash file setting, what happens in the Byzantine setting?
Oh, wonderful question. What happens in Byzantine setting? The answer, the short answer is we don't know. Okay, unfortunately, very not a satisfactory answer. But we believe that there are certain there is a certain common strata across all Byzantine fault-tolerant distributed protocols, right? Like just like convergence is a common strata across all consensus algorithms in a crash fault-tolerant way. There is a similar property, right? That is still yet unknown that we can sort of implement, and that would make the verification and implementation a lot easier. We're working on that. This is just a hunch at this point. So the answer, unfortunately, is I don't.
Yeah, I think it's not so much like consensus versus convergence that
Yes.
This community with Kyber Bell is more
Yes,
also the
yes.
fact that it's actually
Byzantine
Byzantine
fault
fault
tolerance,
tolerance instead
indeed.
of like crash fault.
Indeed, yes, that's a great point. Yeah, that is something that we haven't. I mean, the verification or formal verification community follows quite slowly when compared to the actual implementation. Right? So people go and sort of explore their at the frontiers, and then the math sort of follows later, showing okay, this is how you could do it more simple way, and so on and so forth. So the math is yet to catch up. At least in our world.
Thanks.
It's just a counterpoint to that. There was a paper published 2-3 years ago on the title of BFT CRDT.
Oh yeah, the BFT is yeah. those are CRDT, BFT. Sorry, I'm assuming you're referring to the paper from Klepman, Martin, right? Yeah, that was essentially just CRDTs where you sort of use these secure message passing primitives or digital signatures and stuff like that. So it is still convergence in a Byzantine fault tolerant way, but that's not enough for blockchain. I'm assuming you would need consensus in a Byzantine fault tolerant way, and for that, yes, you guys have a lot of algorithms like Tendermint or BFP, BFT, and all of that. Oh, Byzantine CRDT, yeah, definitely, of course, they do have applications. There's no denying that. But that's a lot simpler than consensus, as it is the case with crash fault tolerance.
So I guess the BFT CRDT idea in this context means that at the convergence layer, you can also provide BFT guarantees.
Yes, certain level of BFT guarantees could be translated, could be provided at the level of convergence layer itself.
Right.
So the actual consensus implementation can be a lot simpler than what it is.
Right. On
So-
top of this BFT convergence layer.
Yes.
Yeah.
Yes. So this sort of insights have been there in the distributed community for a long time. So, for example, in Paxos was quite old, but Raft came along in 2014 saying all of these Paxos implementation have some things in common, which is like leader election followed by things and so on, right? So that's why the title of Raft paper is in the quest of an understandable consensus algorithm and so on. So they tried to factor out the common paths and said, well, this is all. You can factor that out, and it cleanly divides into separate modules and looks nice, right? So yeah, so similar things should be possible in BFT world. We don't know them yet, or there isn't much work there yet.
So it's a new space.
So
An
new
exciting
space.
one.
Quite an exciting one, yes. Yeah, and I'm looking for grad students to work on that area.
Can you just go back? Yeah, on the graphical representation where you've done some benchmarking.
Oh, this one.
So yeah,
This
so
one?
yeah. In
Yeah.
this use case, do you think some ad hoc nature of nodes might also impact this? run?
So, good question. So we've sort of we've looked at multiple ways to explain this, right? But we also done a few ablation studies wherein we sort of added one more round trip time to our algorithm just for the sake of it, right? When we do that, it seems to sort of slowly converge towards what HCD Raft has. So so that seemed to. I mean, again, this is the correct way to do it would be to essentially produce a statistical test and give you a correct value that okay, all these factors is the round trip time that's affecting this difference. We don't have that, but we do have a lot of we did a lot of experiments to rule out the factors like disk latencies or other sort of network latencies and all of that. We controlled for all of that while doing these sort of experiments.
And it looks like the convergence is more faster than the consensus.
No,
in
it's not
every
just
setting?
consensus is convergence is faster. It's about if you have
I mean, not in this setting, but in general, I'm asking.
in general, yes, convergence is faster because you don't have to. It's coordination free because
Right.
you don't have to wait for nodes to agree on something before going ahead. So convergence is generally faster than consensus, but that's not what this graph is talking about. This is about if you implement consensus using convergence. Our hypothesis is you don't lose much. Like you might lose a little bit of performance, but that's not much. But it so ended up happening that we actually gained performance. We have one explanation which I mentioned, which is like we have actually cut down one round RTT in Raft implementation because we did causal consistency and so on. They come with a trade-off, but it so happened that in data center setting, the trade-off worked in our favor, right? Maybe if you do the similar experiment in embedded systems where bandwidth is quite low, it might not have worked in our favor, right? So it's just a different trade-off, right?
Do you see any application where I don't know, like there is an adaptability in convergence to consensus depending on when there are conflicts in the system, then the protocol will switch to consensus, then the convergence. if not.
Yeah, there's a lot of work in that area actually. I mean, I myself had a paper back in 2018 on talking about that. So yes, people have done that wherein it's like, oh, let's sort of try and prove let's write down an application and let's write down the properties the application is supposed to guarantee. Now, can you go and try and find out the minimal set of applications that need minimal set of functions or operations that need to run at high consistency or strong consistency so that your application is still correct, right? So that was a problem that has been posed multiple times, and various people have come up with various answers. I can refer you to a few works on that space. Our work was called Q9, but there are more popular works and more robust ones.
All right, thanks so much.
Yeah.
Any more questions? If no, we can round of applause for the professor, please.
Thank you so much.